So today we're looking at problem 1.5 from Fundamentals of Heat and Mass Transfer. And the problem is consider figure 1.3, and that's here on the side. The heat flux in the x direction is Q double prime of x is 10 watts per meter squared. The thermal conductivity and wall thickness are K equals 2.3 watts per meter K and L equals 20 millimeters respectively, and steady state conditions exist. Determine the value of the temperature gradient in units of Kelvin per meter. What is the value of the temperature gradient in units of degrees Celsius per meter? So we're going to start, as always, with our knowns. And we know that heat flux in the x direction, Q double prime sub x, is 10 watts per square meter. We know that the thermal conductivity is 2.3 watts per meter Kelvin, and the length is 20 millimeters, which I'm also going to rewrite as 20 times 10 to the minus 3 meters, just to put that in SI units for us. So we'll now go ahead to our find, and we would like to find the value of the temperature gradient. So I'll put value of delta T in Kelvin per meter and in degrees Celsius per meter. So let's start with our schematic. And to remind ourselves, I'm going to put that figure here once more. And we're just going to draw a 2D view of this. So I'll draw a kind of rectangular box here. And we're going to have this box with thermal conductivity K. It's going to have length L along the x-axis. I'll also go ahead and draw the x-axis in this direction. And the last thing we're going to have, and I'm going to draw a little squiggly arrow, is our heat flux Q double prime sub x. So pretty simple schematic for this problem. I'm going to go ahead and delete the picture here, and we will move on to our assumptions. So number one, it was told us in the problem, and that is steady state conditions. So steady state. And number two, and we usually have this one, is constant properties. So the thermal conductivity, the length are not going to change. And we can go ahead and go on to our analysis. So under steady state conditions, Q double prime sub x equals minus K dt over dx. And we don't have the Ka like we usually do because we have this double prime here, which means it's in terms of the area. So knowing this, let's go ahead and just quickly rearrange. We want dt dx, so that's what we will solve for. And that's going to be equal to minus Q double prime sub x over K. And that is equal to minus 10 watts per meter squared, divided by 2.3 watts per meter Kelvin. And if you do that math, that is minus 4.35 Kelvin per meter. And the kind of trick question here is this is actually also minus 4.35 degrees Celsius per meter. So since the temperature units here, the Kelvin represents a temperature difference, and that temperature difference is going to be the same in both Kelvin and degrees Celsius, the temperature gradient value is the same in either units, right? So Kelvin is just plus 273, and so if we have degree C1 minus degree C2, that's going to equal, if we want to change this, let's say we have Kelvin 1 minus Kelvin 2, that's going to be degree C 1 plus 273, roughly, minus degree C2 plus 273. And you'll see that the 273's cancel, so it ends up just being degree C1 minus degree C2. I'll put this in a little squiggly box since it's not really our answer. And so for comments, we'll just put one thing here, and that is going to address that our answer had a negative sign in it. And that negative sign indicates, so I'll write the negative sign indicates that as x increases, the temperature decreases. So T decreases. And that corresponds to a positive heat flux in the x direction. So I'll just put positive heat flux in x direction. And that's our problem.